All right, let's jump right in. Today, we're about to become detectives in a scientific mystery, one that's over 100 years old and is still unfolding. We're talking about the devastating puzzle of Alzheimer's disease, and believe me, the investigation is very much still active.
So, this is where it all starts. What can a brain from 1907 teach us about a disease that affects millions of people right now? Well, it turns out pretty much everything, at least at the beginning. The very first clues in this entire case, they came from just one person's brain way back then. And those early discoveries, they kicked off a century-long hunt for what exactly is going wrong inside our most important organ.
So, let's set the scene. It's a story about a doctor, a patient, and a microscope that was about to uncover the first evidence of a crime happening at the cellular level.
Okay, so back in 1907, you have Dr. Alois Alzheimer. He's looking at the brain tissue of his late patient, a woman named Auguste. But what he saw under that microscope, it was anything but normal. It was like a cellular crime scene, just total chaos. He saw two really weird, totally distinct types of damage. He called it a peculiar disease, and just like that, the case was officially open.
So at this microscopic crime scene, Dr. Alzheimer basically identified two prime suspects responsible for all the destruction. And for literally decades, the entire investigation has been laser-focused on these two. You can think of it like this. One is an attacker from the outside, and the other, well, that's an inside job.
All right, let's get a look at our lineup. First up, on the left, you've got beta-amyloid plaques. These are these nasty, toxic, sticky clumps that build up outside the brain cells. Think of it like garbage just piling up and clogging the streets between buildings. And then, on the right, you have tau tangles. These are damaged protein fibers that build up inside the brain cells, basically making them rot from the inside out. So you see, one attacks from the outside, the other gets them from the inside.
And here's where it gets really tricky for investigators. This isn't some quick hit and run. No, this cellular crime is a long, slow burn. These plaques and tangles, they start building up in the brain maybe 10, even 15 years before a person ever feels the first symptom, like memory loss. So the disease is operating in total stealth mode for years, which, you can imagine, makes it incredibly hard to catch in the act. Okay, so we've met our suspects. Now we need to figure out their MO, their modus operandi. How exactly do they do so much damage? Let's start with the plaques. This is basically a problem with the brain's sanitation department. You see, there's this big protein called APP that's always getting snipped into smaller pieces. One of those pieces is called Beta-Amyloid. Now, in a healthy brain, no problem. It gets made, it gets cleared away. But in Alzheimer's, things get out of whack. Either too much is made or not enough gets cleaned up. And this leftover beta-amyloid is really sticky. It starts clumping together into these tough, hard plaques that just gum up all the space between your brain cells.
Okay, now for the tangles. If plaques are a garbage problem outside the cell, tangles are a complete system collapse inside. Your neurons have this amazing internal transport system, kind of like railroad tracks, that shuttle nutrients and other important stuff around. A protein called tau, its job is to be the railroad ties, holding the tracks together and keeping them stable. But in Alzheimer's, something goes wrong with tau. It becomes faulty, it lets go of the tracks, and the whole system just disintegrates. The tracks fall apart. And all that now useless tau protein, it just clumps together into these tangles, literally choking the cell from the inside until it dies.
Right. So in any good investigation, you follow the trail of evidence. And by tracking how these two suspects, plaques and tangles, spread through the brain, scientists have stumbled upon some of the biggest clues in this entire mystery. And this is where the case against tau gets really compelling. Check this out. Where the tangles show up in the brain matches almost perfectly with the symptoms people feel. They pop up first in the hippocampus, which is your memory hub, and that lines up exactly with the first signs of memory loss. Then, as the tangles spread into other areas like the cortex, you start to see problems with language and reasoning. It's wild. The path of tau's destruction is like a perfect roadmap of the disease's tragic journey. But, and this is a huge but, there's a major plot twist. When scientists tracked our other suspect, the plaques, they found something that just didn't make sense. The location of the plaques, it doesn't line up with the symptoms at all. You can have a brain jam-packed with plaques in one spot, but the actual problems, the memory loss, are coming from damage somewhere totally different. This throws a giant wrench in the whole theory that plaques are the main culprit. So yeah,
This mismatch, this massive contradiction in the evidence, it completely flipped the case on its head. And it's led to these huge, nagging questions that have stumped scientists for decades. It's what makes this one of the biggest unsolved mysteries in all of modern medicine.
Which brings us to the big one, the classic chicken or the egg problem of Alzheimer's research. What comes first? Do the plaques show up first and somehow cause the tangles to form? Or is it the other way around? The tangles start the whole mess and the plaques are just a side effect. Figuring out who makes the first move is absolutely critical if we ever want to stop this thing.
For a long, long time, the main theory was pretty simple. Plaques are the bad guys. So, naturally, billions of dollars were poured into drugs designed to just get rid of them, to clear them out of the brain. But here's the kicker. Trial after trial failed. Even when the drugs worked, when they successfully removed the plaques, people's memories and thinking didn't get better. That was a bombshell. It suggested that maybe, just maybe, the plaques aren't the murderer after all. Maybe they're just evidence left at the scene.
These failures forced everyone to go back to the drawing board. I mean, if you get rid of your prime suspect, but the crime keeps happening, you've probably got the wrong guy. Or maybe you've been looking at the wrong version of the guy. What if there's another culprit, an even more sinister one, that we've been missing this whole time?
Well, say hello to our new person of interest, oligomers. So it turns out that before those beta-amyloid proteins clump up into those big, obvious plaques, they first form these small, soluble, free-floating gangs. These are the oligomers. And here's the thing. Scientists now think these are the really toxic ones. They're small enough to move around freely, and they can directly attack synapses. That's the communication point between neurons, messing everything up long before a single plaque is even visible. So with this new, very dangerous suspect in the lineup, the whole theory of the case is getting a major rewrite. And this new focus on oligomers, it's bringing researchers closer than they have ever been to a single, unified theory of what really causes this disease.
Okay, so here's the leading hypothesis right now, the one that seems to connect all the dots. The crime starts with the oligomers. They are the instigators. These little toxic groups attack the synapses, messing up communication between brain cells. This initial attack creates a toxic mess that then triggers our old suspect, tau, to go bad and form those tangles inside the cell. And it's the tangles that actually kill the neuron. So if you think about it this way, the oligomers are the trigger, but the tangles are the bullet.
But, the case is not closed, not by a long shot. Even with this new, promising theory, there are still some huge questions. Like, what's the exact molecular link? How exactly do these oligomers corrupt the tau protein? And what about our genes, our environment? What role do they play in all this? Answering these questions, well, that's where all the cutting-edge research is focused right now.
So when you think about it, we've come an incredible way from one single brain back in 1907 to the super advanced molecular research happening today. The mystery isn't solved, no, but for what feels like the first time, all the clues are finally starting to point in the same direction. And that gives us a real sense of hope, which leads to the final, most important question of all. With every new clue, just how close are we to finally solving the mystery of Alzheimer's for good?